Have you ever wondered how it is we record electricity from the body, this bioelectricity that we've talked a little bit about? How do we actually collect those signals? How do we get them in a clean enough form that we even have something to analyze? That's what this particular lecture is really about to cover. And we're going to use a tool, electronic or a circuit tool, circuit element, that you'll encounter again and again in any circuit. Whether you're building these circuits from scratch or whether you're reading through what they actually contain in a device, you'll come up against this circuit element, this component called an operational amplifier or op-amp. And hopefully you've seen something about these in the book chapter and know something about what I'm talking about. And we're going to dive into some of the details of how those work. Let's jump into measuring bioelectricity first. So what is this bioelectricity? You should be able to have some intuition of this or some exposure already. The ECG is something we've all heard about. It goes back about 100 years. This image shows, again, an image from around the turn of the last century. Those big buckets are actually the electrodes, and the white lines on the chest of that poor innocent victim suggest a way to interpret those signals, and that we won't get into this particular time. But those are 3 electrodes. They don't look like electrodes you've typically seen in the hospital if you've ever been exposed to them, or any lab you've ever done. Things have gotten a little more streamlined since then. They've also gotten a little more complicated in that we record not just from 3 different locations, but from multiple locations. In this case, 6 locations on the left side of the chest, occasionally similar symmetric locations on the right side of the chest. And from these electrodes, we can then feed the differences between electrodes into a recording device and capture what is the standard ECG. And at this point, it is what's called a 12-lead ECG. That's the term you can look up and that you might hear in the hospital. Now, of course, being engineers, it wasn't long before people, actually in the 60s already, started to expand this notion of ECGs and said, I don't want to know just what's happening on this left side of the chest or maybe the right side of the chest. I want to capture information over the entire torso. And out of that emerged a technology called body surface potential mapping. So we're mapping, as in we're covering some area with sensors, in this case ECG electrodes, and it's like capturing a topological map. You don't build a topo map based on 6 different electrode locations or 6 different altitude sensors, right? You go out and you measure at many locations, and out of that you create a map. And so this technology is called mapping generically. And we can map on the body surface of the torso, the thorax, and there we're mapping the bioelectricity coming from the heart. We can also map on the surface of the scalp, on the head. And here you see a cap, a pre-made cap from a commercial company that cannot include up to even 500 electrodes, 256, not that unusual, to again map the entire surface of the head and capture, measure the signals from the brain. They contain information we can use to diagnose and deal with patients. We can also put electrodes inside the heart. There's times when that's very necessary to pinpoint sources of abnormalities. Those electrodes are often mounted on catheters, which are slid into the body through small incisions somewhere in the arterial or venous system, typically either femoral or somewhere around the neck area. And so we can thread these electrodes, and what you see here is an image of an anatomical structure called these are actually the 2 left and right atria, an anatomy derived from images, from MRI images. And superimposed on those, you see little cartoons of the electrode placement. So these electrodes are capable of broadcasting their location to a computer, and the computer reconstructs their location inside the heart. It's fantastic technology and is very much where biomedical engineers work and play and do their research. So those devices exist. They're used routinely in our hospital, something we can talk about more if you're interested in. Here's the device you really need to know about, being from Utah. This is called the Utah Electrode Array. It was invented by Dr. Richard Norman, now a retired colleague of ours in the department. And Dick created this electrode array with the idea of having a very small scale electrode that he can plant in the brain. So these are not surface electrodes, these are implanted right in the brain and other elements of the nervous system. And on the right you see an image of Dr. Greg Clark, and he is the inventor, the scientist behind what's called the Luke arm, which you may have heard about. If not, you should check it out. There's some very cool videos describing that pretty amazing sensory device that they have that allows an artificial limb to sense pressure, to actually be able to feel things. And a lot of that technology is really based on these Utah electrode arrays. More importantly, you can see by what he's holding in his hand that this is a really small electrode. And of course, it gets implanted into the brain or nervous system tissue. So all these are sources of bioelectricity. There are lots more I'm not going to talk about. So this is a ubiquitous need that we have in biomedical engineering to capture the signals that come from the body and record them in a way that we can actually do something with them. So how in the world do we do that? Let's start with a schematic view of things. So here's a very cartoony version of a body. You can see the heart in the middle there. You can see that same triangles that we saw drawn on that photograph of the poor grad student. And you see the electrodes are mounted here on the left and right wrist and on the left leg. And this is the most basic kind of ECG that we typically do. And the question is, how do we record those signals? How do we picture signal recording happening here? So this is now the schematic that we'll see again and again. It's the classic measurement schematic that describes capturing bioelectrical signals. And you can see it has two resistors, RE and RM. RE stands for the electrode resistor, and RM stands for the voltmeter resistor. So what's that? So on the right hand side you see this circle with a V in it. That's a voltmeter. It's a symbol for a voltmeter. It measures volts, obviously, but it's an ideal voltmeter. So it's perfect. But of course nothing's perfect. So what does a non-perfect device look like? Well, it looks like a perfect device in parallel with a resistance, which we're calling the measurement or RM resistance. So the two of those things together form a schematic representation of a real voltmeter. Okay? So that's the circuit we're dealing with. Now, we want to measure the signal that I've labeled here as VECG. That's our goal. But the signal we actually measure is VM. And you can see there's some stuff in between. There's the electrode resistance, which sadly we don't even know. We can try and minimize it or maybe guess it, but that resistance consists not just of the electrode itself, but also the interface with the skin and the skin itself. And that varies from person to person. It varies based on our state of being, actually. This is actually the basis. Some of these variations in skin resistance are the basis of lie detection. So it varies in somewhat known ways, but not in an easily quantifiable way to account for or assign a value to RE. So RE is fundamentally an unknown that we don't know the answer to, and that will become important, as we'll see. Now, we can analyze this circuit using the tools you already have learned. We can do a Kirchhoff's tour. So here's a Kirchhoff's tour of this simple circuit. And if we go from counterclockwise, starting from the lower left corner, we can write down the equations as the sum equals 0 of that VECG signal that we're trying to measure, and we encounter the negative end of that signal first, so we draw it with a negative sign, and then we have a current that we've drawn in the circuit I, so that means that we encounter the positive end of RE and the positive end of RM, so those both get positive terms, and we can write down that simple equation. You should recognize this by now. And then we can solve it in terms of the actual current. That's nice, we know the current, but we actually need to know what the measurement of the voltage would be in this situation. So we know the current that goes through RM. Now we can also calculate the voltage across that RM. That's just I times RM. We have I, we multiply it by RM, we simplify the expression, and we get this. The measurement voltage measured by our ideal voltmeter is the product of this combination of resistors and the actual voltage that we're trying to measure, the VECG. Now, in a perfect world, you would say, well, I want my measurement to be the same as VECG, and I don't want to distort it by this ratio of resistors here. And to top it all off, I don't even know the value of RE. I can't tell you what RE is. There's no way to predict that even. So I have a complex situation here. And I have to figure out, what the effect of that combination of electrodes would be. Now, I can picture that the best case I could hope for is that RM is large compared to RE. And then I'd have RM over RM, and then I'd have 1. So the maximum this value can take on is 1. Otherwise, it is a number smaller than 1. And I can make it in my favor as close to 1 as possible if I make RM as large as possible. And that's what we do with the devices we build. We make the input resistance for our voltmeters as large as we feasibly can. in order to reduce the effect of RE, to negate the effect of RE, to in this equation, kind of make it relatively go away and get as close as we can to this value of Rm. So at least then we don't get attenuation of what are already small signals. We'll come back to that too. So that's the best scenario we can count on. Now this expression of a voltage times this ratio of resistors like this Rm over Re plus Rm, that's also a configuration we're going to see again and again in this course. And we call it a voltage divider. Why voltage divider? Because we're dividing the original voltage VECG over the two resistances through which the resulting current flows. We're dividing the voltage across Re and across Rm. And the component we see here is the component across Rm. So we've divided the voltages into two parts, that voltage into two parts, and we can say here's the voltage for what we call Vm, the voltage across Rm. We could just as easily replace Rm with Re and say that's the voltage that drops across the electrode resistance. And this configuration of voltage divider, again, we'll see it many times in many circuits. Very common. It's all kinds of useful features that we'll actually observe in the circuits that we deal with. But back to this problem that we're having of measurement here, because even in the perfect scenario, that ratio is always going to be 1 or less than 1. So that means that these small signals, the VECG, which it turns out is on the amplitude, on the order of a millivolt or two, the best scenario I can hope with in my voltmeter is I can measure a millivolt. And that's a pretty small signal. And if it's a signal from the scalp, it's orders of magnitude smaller. There we're talking about signals in the order of microvolts. So these are a millionth of a volt. These are very small signals, and it's hard to convey these signals, transfer these signals, transmit these signals without there being some noise introduced, and that noise distorts the signals and may even wash the signals away so we can't even see the useful information. So we need to do something first before we actually use the output of this simple measurement circuit. And of course what we need to do is amplify the signal, right? Should have seen that coming. So what I want to do now is introduce an amplifier, that little triangle with an A in it, that says, I'm going to amplify this signal. How does that change my equation? If we go through the Kirchhoff's tour again, with the understanding that A just multiplies the input and the output is larger by that factor A, and that the A is a number larger than 1, then we can write a circuit down that looks like this, that says the output voltage that I measure, the Vm that I measure with the voltmeter, is equal to still the voltage divider part. That doesn't magically go away, but I can balance it out by adding in some greater than 1 amplification in the term A multiplied by VECG, and now I can get a signal Vm that's actually larger than the original ECG or EEG or whatever signal we're measuring from the body. So this is really useful. As long as I make the ratio bigger than 1, I have a useful circuit. So that measurement circuit we'll see a couple of times. It's really common across all measurement scenarios, and it leads naturally to a number of things. One is, how do I reduce Re? How do I make it as small as possible? How do I make Rm as large as possible? So a bunch of these sorts of tricks that we can spend a little bit of time talking about, but that's not really the point of this course, become very important in the biosystems course, because we want to focus on the amplifier part. How does that amplifier part work? How do we make amplifiers? The core of most bioamplifiers, amplifiers that multiply biological or bioelectric signals, is what's called an operational amp or OpAmp. And you've read about those in the text, hopefully, and now we're going to dig down a little bit into the OpAmp. Now, my perspective on OpAmps, and I first learned about them as an undergrad, just like you are, and when I was first encountered them, I thought, this is crazy. This just defies what I thought I knew about physics and reality and energy and all those things then. So there's a certain aspect of magic to OpAmps. So I actually think OpAmps are magic. And I like to use the metaphor of Harry Potter and Hogwarts and the magic that goes on in those wonderful stories for what OpAmps do. And the reason is that there is magic in Harry Potter that makes no sense, that you would not believe, and that is not true. But the magic is not unlimited. There are certain constraints that the characters always had on what they could do and couldn't do. And if they learned enough spells, they could do more things, but there were certain things they couldn't do. They couldn't routinely bring people back to life or make injuries go away or make people bulletproof or these sorts of things. So that's a little bit like what goes on here. There are magic elements in OpAmps that we will learn about, and we can use those OpAmps to cast our version of spells, that is designing circuits that leverage those magical characteristics of an OpAmp and use it to do good. So let's deal with some of the ordinary parts, get those out of the way, then we get to the magic part. So the ordinary parts are, we need a power supply. We need to feed power into these things. They convert energy that's coming out of the wall or out of our power supply or our batteries into the output that we care about, the sound that we send to our speakers, the large signal we record from somebody's ECG. They have inputs, they have outputs. Those are obvious. So those are pretty much expected things that you would always have. Something special about the input in this particular case is it's called a differential input. Differential input means that it always magnifies or amplifies the difference between the two terminals. And we call these terminals the inverting and non-inverting, or plus and minus, depends on terminology. And our amplifier always takes that difference and multiplies it. So in case you come across that term differential input, that's really what it means. So then we have the differential input, we have the power, we have the output, and we have an op-amp. And you can see there's a little picture of one here from a company called Burr-Brown, that's the BB stands for, and there's a model number on it. We'll see that in just a sec too. Now what you see is the schematic diagram that we use to express the behavior of an op-amp. So inside an op-amp are many components. It's not a simple device. Just the op-amp, even though it's pretty small, it's not a simple device. It's complicated in and of itself. It's complicated to make magic happen, which shouldn't surprise us. So we can treat it though schematically as it's described here. So this is sort of the mapping between the physical device with inputs and outputs and power supplies and the schematic version of it. And we see there are some key features in that schematic we're going to talk about. One is the input resistance, this Ri, the output resistance, Ro, and the amplification factor, A. Those are three things that we're going to see can be magical in an op-amp. But that's the description of the device in its sort of functional state. And everything we do is built on that functional description, which we'll be able to simplify based on the magic. So again, a little more practical things. There are schematics for these devices. They're packaged in these little plastic dual inline devices or dual inline pin devices. They have numbers on each one of the legs. If you're going into the lab to build these circuits, you have to keep track of all these pin numbers and make sure you put them in the right place and connected the right wires to them, for obvious reasons. And on the right-hand side, you see the packaging diagram for these two different brands and models of op-amp, one of which contains a single op-amp, the other which contains two op-amps in the same package. So, it's nice. It's a little more efficient, a little less size. Can be helpful when you're trying to make small devices. So now we get to the magic part. This is the cool part. So what's magic about an op-amp? If we go back to our functional schematic of the op-amp, remember I said we have input resistance, output resistance, amplification. Magic number one says the input resistance is infinite. Sure it is. How do we make something infinite? And what does infinite mean? I'll show you what infinite means in just a sec when we look at the specs of a typical op-amp, but it's pretty impressive. So we have that bit of magic. I'll call that magic number one. Magic number two is the output resistance. The Ro is 0. So this thing doesn't waste any energy. All the energy that comes out of the amplifier goes right out to the output, doesn't flow through that resistor, or that resistor is 0, so it doesn't consume any energy. And wouldn't it be nice if that were real? It's not real, but it's pretty close to real. And the numbers achieved are very close to 0, as it turns out. It's maybe the least magic, or maybe the magic that's easiest to accept, because the third magic is really hard to accept, and that's that the A, this amplification value, is infinite, another infinity. Right? Zeros we can handle, infinities are always a little sketchy when it comes to real devices. So let's assume for the moment those are real, as in those are viable and close enough to reality that we can trust them. What does that do to our functional schematic? Well, it simplifies it pretty dramatically in important ways. We get a new schematic that looks like this that we're going to call our ideal op-amp. And the ideal op-amp doesn't have a connection between the two inputs. That may sound totally bizarre, but if the input resistance is infinite, then that's functionally what we have. Similarly, on the output side, there's no Ro anymore. It's gone away. And even A's gone away because we don't care about A in a perfect schematic ideal op-amp. And so we should be skeptical, of course. We're engineers, we should be skeptical. So let's look at an op-amp, the kind that you would use in the lab. These are cheap, a couple of dollars a piece kind of op-amps that you would be using in the lab to build a circuit. This is the LF353N from Texas Instruments. Now, if we look down to the table, there's lots more schematics I'm not going to, or lots more specifications I'm not going to show you here, but let's focus on two of them at least that are important to us. One is that input resistance. We look carefully, input resistance, and there's a temperature spec that goes with it. That's not unusual in electronic components. And if we look at the typical value, that's what tip means, the TYP, typical value 10 to the 12th, and way over to the right, ohms. Oh my goodness. 10 to the 12th ohms. I don't even know what the prefix is for that. That's an enormously big resistance. When we think that electrode resistances, which were important to us, they were on the order of kilo ohms to maybe mega ohms. Not unusual to have a few mega ohm resistance. This is a million times bigger. A million times bigger than the biggest resistance you'd typically ever find or use or encounter. So this is big. This is close enough to infinity for us to treat it like it's infinite. This is not too much of an exaggeration in practical terms. Now the second value is the A value, the amplification value. And there we see again, there's different specs, different conditions, give you sometimes different numbers. You can drill down more and more on these things to get more detail. But the point is that here are a couple of numbers for you to look at under standard conditions of a minimum value of 25 and a typical value of 100. And you might say, well, hey, 100, what's the big deal about 100? That doesn't sound like infinity or even close to infinity. But then we look at the units, and those are volts per millivolt. So what we really have is an amplification of 100,000. And that may not be as close to infinity as 10 to the 12th, but it's pretty big, especially when we think that the amplifications we're trying to achieve are on the order of 1,000 maybe, but not 100,000. So this has got the specs that are close enough to magic for us to treat this using those magic numbers. And that's what we're going to do. So now I'm going to walk you through an example of how we build a simple circuit, and then more importantly, how we analyze that simple circuit using the techniques you'll see again and again, and you'll practice in the homework assignment. And there'll be a separate video that goes into another example that will cover this more completely even. So here's the example. It's an amplifier. The triangle is the amplifier. You see there's a negative and a positive input, or the inverting and non-inverting inputs. We see you have a source there, that's Vs. We have a source resistance, Rs, and we have what we call a feedback resistance, Rf. Why feedback? Well, if you look at the way it's connected, it's taking the positive output and carrying it back to the negative input. Now, that's incredibly important. An op-amp without that sort of connection will not function. This is how we take that very big value of A and control it. Control the actual amplification that we get. Because we want to control the amplification. We want to set a certain value of amplification. Maybe we want to have a knob, like a volume knob, to alter that amplification. So these resistors have to give us the way to do that. That's what we're going to set out to prove. Now, the question here is, what is the amplification? So what's the ratio of the output voltage to the input voltage, or V0 to Vs? That's the goal of this whole project. Good to keep that in mind. So now let's swap out that diagram for the schematic diagram. There we see the schematic diagram. Let's assign some currents. I'm going to call IS the current from the source. IF is the current that's the feedback current. Immediately that determines the pluses and minuses around those resistors. I'm going to build back in the A, we'll see in a second how I can make it magically go away again. But the output here, I'm saying the output voltage in this circuit is A, which is a big number, times the difference between the positive and the negative inputs, Vp minus Vn, or the non-inverting minus the inverting input. So that's the circuit we're going to start with. Now we look at that circuit and we say, well, we have taken advantage of one piece of magic. Anyone recognize what we have taken advantage of? It's the fact that the input impedance or input resistance is infinite. There's no connection between the two inputs, Vn and Vp. That means that the current that I've called Is flows completely up and over the amp through the resistor Rf. And that means that if I look at that node A and write down the scenario at node A, then I find that Is is equal to If. Those currents are the same, which means I can already get rid of a current. So I've kind of used that scenario to simplify my equations even before I've started setting them up. So now I can start to apply, again, the Kirchhoff's analysis using magic number 1 to get rid of, or set these two currents equal to get rid of the input resistance, make it infinite. And now I can start to set up some Kirchhoff's tours, just like you've done before, just with some unusual components in the mix. So let's draw a Kirchhoff's tour as we have here, this KT0 I've called it. And we're going to use that to really let the magic sink in, to get the impact of the magic on this circuit. You could do this for any circuit, obviously. So we're going to ignore the RF, RS for a minute and look at what we have here. So this is like a Kirchhoff's tour that includes the output of the circuit. And we can write down from that tour, if we do the loop, we have a minus A. You look at the minus sign is at the bottom of that little diamond-shaped amplification. Remember, the diamond is a controlled voltage source. You've seen that vaguely maybe before. And we know the output of that voltage, or the voltage that that device generates, is minus A times the difference Vp minus Vn. Then we go through the current I/O across R0, that's another voltage difference, and then we have the voltage difference in the output. And the pluses and minuses are set up so we get positive signs for those two voltage terms. So we write down this Kirchhoff's tour expression that contains the amplification, the difference between the two input voltages, and this term I0, R0, and then the output voltage. Now that term I0, R0, we can use magic step number 2 to set that equal to 0, because R0 is equal to 0. So that gets rid of that term. And then what's left over is this Vp minus Vn equals the output voltage divided by A. And as A gets big, which is magic number 3, we can say that Vp minus Vn is going to get close to 0. And that means that there's no voltage difference between Vp and Vn. They're the same voltage. And we will use that heavily every time we analyze a circuit with an op-amp. So once we've done this part, we really never have to include this particular tour again. We've by setting, letting the magic work, we really, as you'll see, won't need to do this particular tour again. We'll have other tours we have to do. So let's get back to our original question. Here's the original circuit again. Now I have my KT1 is my input Kirchhoff's tour, KT2 is my output Kirchhoff's tour, and that's how I'm going to analyze this particular circuit. And I'm going to make use of the magic that I already have, that IS is equal to IF. I'm not going to need that A, and the R0 is equal to R0 is equal to 0, so I can get rid of those terms when should we encounter them. But we actually won't encounter them because they don't even show up in the Kirchhoff's tours that we're doing. The tours don't even include that, what we used to call KT0. So from the input side, and we always have to make sure we have a tour that includes the input and a tour that contains the output. And you will see in the video on solving op-amps that we can do multiple different types of solutions. So we can take different Kirchhoff's tours and solve the problem different ways. We just need to have two tours with problems with this level of complexity, because the current is a single current here. And with one current and the two unknowns, the Vs and Vo, we just need the two equations. So now let's solve it. So KT1 gives us this equation. Again, look at this yourself, make sure you can convince yourself that that's the right equation that you would get. The part I've made use of here explicitly is I've said Vn minus Vp, but we know those are the same. We know that difference is equal to 0. So now we can simplify that expression even more to be something like this. This is just rewritten a little bit to say that the current Is is equal to that ratio of the voltage at the source and the resistance at the source, Vs over Rs. Now we have the current that we need. Now let's look at KT2. So that now follows up over Vp and Vn. And we know Vp and Vn have the same voltage. There's no voltage difference between those two. So that doesn't actually contribute anything to our Kirchhoff's tour. Instead, what we have is the current through the resistor, which we initially called Rf, and then the voltage at the output, which is V0. Those are the only two terms that contribute voltage to that Kirchhoff's tour. Now we know already that If equals Is, so we can rewrite it as Is times Rf. And now we have Is on the left and an Is on the right, and we can substitute. So we do a substitution from left to right. Doesn't matter which way you do this. I like to do it this way. I like to set these up this way with one Kirchhoff's tour and then the other Kirchhoff's tour next to it. Allows me to see where I'm going and how to simplify. So I substitute the Is in there and rewrite the equation to look like this. Then I do another simple rewriting of it again, put the V0 on the left because that's our output. So now I want to see this ratio between VO and VS, and we see that we have this expression here. So this says the output voltage is the inverse product of the ratio of the feedback resistance and the source resistance multiplied by the input voltage. Now we can look at that, and you should get used to doing this, looking at the results of an analysis and saying, what does that tell me functionally? What kind of functional purpose does that amplifier have? And the first thing we look at is we say, well, it's inverting. There's a minus sign. So if I feed 1 in, I get -1 out. So that's an inverting aspect to it, which may or may not bother me. And then I have the amplification factor, that A that I was looking for before, right? The A of the whole amplifier from my bioelectric measurement circuit. And that's going to be this ratio of the feedback resistance and the source resistance. So this gives me a very simple way to tune or set that amplification that I need for my application. Now you could say, well, this inverting is a pain. How am I going to deal with this? Well, you can imagine, for example, having 2 of these, plugging one into the other. And so the output of one would be negative, and you plug it through another one, and it would turn it back to positive, and you'd still have the whole circuit would give you the positive version of your input, and you could spread the amplification out over the 2 amplifiers if you wanted, or the 2 circuits. So lots of flexibility in how you lay these things out to solve whatever problem you're trying to solve. So that's really our answer. One thing to note in that answer is, of course, that A, as in the amplification of the amplifier itself, the op-amp itself, that's gone away. We use that magic of A being really big to make it unnecessary to include it. It has consequences on the values of the voltage difference between Vn and Vp. It allowed us to say that Vn is equal to Vp. So that's where we took that A into account. Now, this may seem all very convoluted, and it will require some thought if you really want to work through all the details, and there's certainly lots of things to read on it, but we don't really have to do that. All we really have to do is follow a set of steps, and we can analyze and build a lot of really cool circuits. Once we accept the magic and the consequences of the magic, just like learning your spells at Hogwarts. So you're going to learn some circuit analysis spells that are based on this magic and be able to eventually, well, analyze initially and eventually build some very useful circuits. So what we did, just to recap, to analyze this circuit is what we're going to see in subsequent videos. And there's a set of steps that you'll see you'll apply again and again. So this is like the recipe almost for solving these kinds of circuits. The first thing is to replace the amp in your initial circuit with that schematic, right? That's an obvious one. Then you do what you always do in circuits. You pick a current direction, and then you mark the plus and minus signs over the resistances that are going to go into your Kirchhoff's torrs. Then you select a Kirchhoff's torr that includes the input, at least some part of the input or the input voltage, another Kirchhoff's torr that includes the output. And again, as you'll see shortly, there are multiple ways to do this that are slightly different, but give the same answer. And once you have those, then you can write down the Kirchhoff's torrs. You solve for the current, because you want to get rid of the current, because you want ratios of voltages here. So the current is how you connect these two resistors, or excuse me, connect these two equations, just like we showed you before, where I had an IS on the left and an IS on the right, set them equal to 0, IS disappears, I have everything in terms of voltages and resistances, and that's what we need to achieve. So if you have a current flying around, if you get to this step of combining things and trying to find an answer and there's still a current term, then you've done something wrong. Guaranteed you've done something wrong. There's some other information you haven't taken into account or some other algebraic step you haven't conducted properly. So we set those two currents equal to each other, or what's on the right-hand side of those two currents equal to each other, and then solve it, and then we're good to go. If we have numbers in the question, if the goal was to say what is the amplification factor of a particular amplifier, and some questions will have those, then you just plug the numbers in. But you plug them in at the end, and that's a pretty easy step. Your calculator will handle it in no time. The key here is, as with all these kinds of problems, not to plug the numbers in too early. That runs the risk of you losing track of variables, forgetting variables. You can't do a unit check when things are in numbers. You can only do implicit, let's say, unit checks when you can see what you have there, that's an R there, there's a V there, you know, whatever. You can do unit checks when you know the variable meaning in terms of what quantity it's ultimately will contain. But when you put the numbers in, that information becomes much harder to track. So leave it in terms of variables. In fact, lots of times we'll just ask you for numbers in terms of variables. And when you need to, plug the numbers in at the end and get the answers you want. But the goal is always to figure out what is amplification, because these are amplifier circuits. We're designing amplifier circuits. And they'll get more complicated. They may have multiple sources. There's all kinds of funny things we can do to create certain characteristics in an amplifier circuit. And so that's the variations you'll see when you go to solve the problems in the homework and the problems on the exams. But the steps will be the same. And this week we'll practice those steps. And shortly, hopefully you'll watch the video that goes through another example of an OpAmps and shows you 3 different ways to actually solve it, which also says that's how you practice. You solve the circuit different ways, using different Kirchhoff's tools, using different assumptions of current direction. You'll find many, many different ways to solve the same problem, and each one will teach you something, and you'll get more comfortable, more confident, more practiced, and be able to do a better job at solving these. Now, you will learn other techniques when you get into biosystems, for example. In fact, if you came from an electrical engineering background, you may even already have learned new techniques. That's all well and good, and those techniques are useful. Sometimes they're good for computers, even though they may not be that intuitive for humans. This is a technique we'd like you to use. We'd like you to build up a solid skill, use these Kirchhoff's tools. There are lots of times when this is enough of an approach, if you know how to use it. It's arguably simple to do, and it does lead to accurate results, just like any of the more complicated or sophisticated methods. So please stick with this approach. Use it. That's what we're looking for. That's what we expect to see. If we don't see it, that's not considered done or correct. So stick with this approach. It does work in real life. We've built circuits using this kind of analysis tools that are implemented in systems we use in the lab all the time. So this is not far-fetched or stupidly simplified. This is a very viable approach, and will give you ultimately a lot of intuition of how the system works, and that's also very important. So hopefully that was a tractable, understandable explanation to the magic that is OpAmps, and we look forward to your questions about it, and hopefully you'll quickly try it out, see how it works, and let us help you figure out how to solve these things. And recognize that they really form the basis of amplifiers used every day in the hospital, in our labs, in R&D and companies. So really is very practical. So thanks for your attention. See you soon. Take care.